Okay, here again we have our x squared function, our toolkit squaring function, and our 4x4 square. I can't get one call it a rectangle. It is a rectangle. Okay. What I call a fundamental square. What we want to do is we want to transform this graph to a 4x8 rectangle. In other words, we want to take this 4x4 rectangle and make it into a 4x8 rectangle. And we do that by moving every point twice as far from the x-axis. Okay, so what does that mean? Well, if we move this point twice as far from the x-axis, how far is it going to be from the x-axis? Again, stop and think about that if the answer isn't obvious. If that isn't obvious, how far is this point from the x-axis? It's 4 units from the x-axis. If we move it twice as far, it's going to be 8 units from the x-axis. Now, 8 units from the x-axis, that could be down here 8 units. That'd still be 8 units from the x-axis. Implicitly, we're going to move it on the same side of the x-axis, okay? So we're going to move it to the point where it's 8 units, meaning that it's going to move, well, it's 4 units from the x-axis. Now, the other thing that's kind of implicit here is we're not going to change the x-coordinate, okay? So we could say without changing its x coordinate. And same side of the axis. This case, those things aren't clear. Okay, well, we're 4 units. We're going to have to move up here. So now, this is 8 units from the x-axis. And yeah, here's our new point. Okay, so this point moves here. Okay. Well, where then would this point go to? Well, it would move twice as far. Okay. So it's this far. It's going to move to here. Now, which point moved further? Well, the one that was further from the x-axis to start with, because we're going to double its distance from the x-axis. Okay, make it twice as far from the x-axis. So if a point's closer to the x-axis, it's not going to move as far. Now, what we want to do, of course, is we want to understand what's going to happen to points on the graph of the function. Okay? Because moving the whole, we're moving all the points within the square twice as far from the x-axis. Well, a lot of times I'll indicate this kind of movement by a vector, an arrow. That arrow shows how far it is from the x-axis. An arrow of equal length will show where this thing's going to end up. So it's going to end up like here. And I'm going to use purple chalk to indicate the points that we're going to get for the points on the graph of the original function. Okay. Now let's finish with the rectangle. Obviously, this point is then going to move up here, and our new rectangle is going to be quite short. There's our 4x8 rectangle. Here's a point on the transformed graph. This is another way of transforming a graph. Okay. This point is on the graph of the function. So we can kind of make it perfect. This point is on the graph of the squared function, so we'll make this perfect. Now, what about the origin? How far is the origin going to move? Because we do have the point 0, 0 on the graph. How far is the vertex of this parabola going to move? Well, how far is it from the x-axis? Distance is 0. If we double the distance, we double 0, and we still have 0. So we see that this point is going to remain here. Okay, let's just take another random point. Let's take one here. Where's that one going? How am I going to draw that? Similar to what I did over here. You ought to have a copy of this. You ought to take a minute and draw that. If you got really good visualization skills, you can see where it's going to go. You can see how this is going to happen. But here we go. Okay. This is how far the point is from the x-axis. We do another arrow of the same length, and coincidentally, I didn't really choose it, so it would be, but it looks like it's going to pretty much end up right here. Okay, so there's another purple point. Well, we've got purple points here, 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 and here. So we can through those purple points. And now, any point that we might care to choose. Let's say this point on the graph is this far from the x-axis. If I do an arrow of equal length, it should get us up to the purple graph. Okay, I can draw arrows from the x-axis up to any blue point, and if I match that with another arrow on top of it, it should end up on or near the purple graph. Now, this is a hand sketch graph. Actually, I think I did a fairly good job with these, but that's unusual, so enjoy it while you can. Okay, there we have it. So we have a new function. Okay, now this function is going to be y equals g of x. How would I write that in terms of f of x? Well, think about it. Might be obvious. What happens to the y values? What happens to the y values of the f of x function? When we stretch this thing out by a factor of 2, when we move every point twice as far from the x-axis, the y values get twice as great. And if y equals g of x, well, on this function, y equals g of x, that's twice what f of x was. So that's f of x. Now you can do the table. Your standard table scoring function, which incidentally you need to be able to do. Very quickly. Then what happens to g of x? Forgetting the fact that I said g of x was 2f of x. Our definition of g of x is it's the function you get when you move every point of the f of x function twice as far from the y-axis, or from the x-axis. Well, how far is the point -2, 4 from the x-axis? It's 4 units. Right there it is. It's 4 units from the x-axis. It's going to end up 8 units from the x-axis. Okay, matter of fact, in every case, the y-coordinate is how far you are from the x-axis. me write it out. Put in calculation. Okay, again, this point was 4 units from the x-axis because that's what the y-coordinate is. It's how far you are from the x-axis. Okay, if we are 1 unit from the x-axis, then we're going to end up with the geometric function. 2 times 1, which is 1/2. If we're 1/4 of a unit from the x-axis, okay, what are we going to get? We're going to get 2 times 1/4 equals 1/2. If we're 0 units from the x-axis, we're going to end up twice that far. Twice 0 is 0. Okay, and then we can okay. So there's a table. Now, if we don't believe the g of x is 2f of x, and let me should have had a little more foresight in what I labeled these columns. We'll call this y equals f of x equals x squared. Okay, so again, saying that every point moves twice as far gives us these values. We don't have to know that g of x is 2f of x. We're trying to test for the g of x equals 2f of x. Okay. Well, if f of x is 4, then 2f of x is 8. And 2f of x and g of x are the same thing. Okay. It might not be totally clear why I said it the way I did. Let me attempt once more. The way we defined the function was move every point twice as far from the x-axis. Interpreting this column, first of all, as how far we are from the x-axis, this is what we get, twice as far from the x-axis. So this column, all the way down, gives us our distances from the x-axis. These numbers then are double the distance from the x-axis. We could also say that these numbers are the values of f of x. And these numbers are double the values of f of x. And these two things are equal. Double the distance from the x-axis is the same as double the value of f of x. If you understand that totally, then you understand how this works, and you'll be better able to apply it to other functions. I'll say we could then move this graph someplace. I don't have room to move it here, but I think I'll probably do that. I'll clear out a little bit more space and just indicate how that would be done. Okay, so here we have the same situation I have over there. Without doing a lot of labeling, I'm going to sketch my f of x equals x squared graph. And my g of x equals 2f of x graph. For every point here, moves twice as far from the x-axis. And I'm actually going to draw a few arrows here. Let's see, it's one arrow here, goes up here, an arrow here. Might go up to about here. And that's really too long. There it is. Okay. An arrow here. Might go this long. And of course, this one. And all the way up here. And this one ends up here. So we have points on the graph of the g of x function. And we then sketch these parabola. Yeah, that came out fairly well. Okay, there we are. Now, what I want to do is, I want to do the graph of the color. Come on, okay, here with me. Okay, I want to do the graph of I'll call it h of x equal g of x minus 8 plus 3.3. Now, I made a little sneaky. If I do, I've got the g of x graph, what I have to do to get the graph of g of x minus 8 plus 3.3, kind of turning something we've done around in a little different context, in a little different order. Okay, you might want to stop and think about that for a minute. You might get it, you might not. I'm going to tell you in a minute. I recommend you pause and think it through as best you can. But I'm going to tell you now. Okay, we've replaced x in the g of x by x minus 8. We've replaced, and then we've added 3.3. Okay, that means we move the graph horizontally 8 units and 3.3 units vertically. So, draw a little arrow here, a little arrow here. There we go. And now I can sketch my 4 by 8 rectangle. I've got just enough room to do that. Going to be this wide. And I'll be a little careless. I'm not being real meticulous about it, but if you are meticulous, if you have a tendency to want to be meticulous, then do this as meticulously as you like. But also be able to just kind of slop it down so you see what it's going to be like, and then refine it and make it pretty if that's your inclination. Just slopping it down reasonably well is pretty much sufficient as long as you know where the points are. Okay, so we'll see what I mean by that. And now it's about this wide, it's going to be about this high. It's going to come up pretty close to the top of the board. There it is. And we see what shape it's going to have. So we can kind of draw it in. Okay, so that should be it. Now we want to be sure we understand what these points are. What's this point? What's this point? Well, 2 ways to understand it. From the origin to this point, we've got to move 2 units this way and 8 units this way. Well, here we're at x equals 8. We move 2 units this way, we'll be at x equals 6. And if we move up 8 units, well, 8 and 3.3 is 11.3. It doesn't hurt to go ahead and show here's 6, here's 10. You kind of know that. from what we did before, but it's a little different rectangle. So what we're saying is that this point ought to be 6. And since it's 8 units from here up to here, and this is 3.3 units from the x-axis, we're at 11.3 units from the x-axis. So we have 6, 11.3. And those are the coordinates of this point. And similarly over here, think about what are the coordinates of this point. Pause if you need to. Think it through because you learn a lot more that way. Okay. Well, anyhow, the coordinates of this point are 10, 11.3. And of course, the coordinates of this point are 8, 3.3. And you can figure out the coordinates of other points. Take the points on the graph of the toolkit function. And of course, we have a table here. Okay. Take the points we get from this table for the g of x function or the 2f of x function. And add 8 to all the x coordinates. And you're going to get the coordinates that correspond to the transform graph, to the shifted graph. And then add 3.3 to all your y coordinates. You get your 11.3 here and here. You get your 3.3 here. Okay. Okay, well, there it is. But now let's see. Let's take this a little further. H of x is g of x minus h plus 3.3. Now, what's g of x minus h? G of x is 2f of x. Okay, so if I replace x here with x minus 8, if we want to get g of x minus 8, we've got to replace the x in the g of x function by x minus 8. Then we're going to have to replace this by x minus 8. Okay, so this equals okay, well, g of x equals 2f of x. So this is going to be 2f of x minus 8 plus 3.3. Okay. And of course, what's f of x? F of x is x squared. So what's f of x minus 8? We replace x by x minus 8, and we get 2 times x minus 8 squared plus, and chalks right there, plus 3.3. And now if your algebra is up to it, see that h of x equals 2 times x minus 8 quantity squared plus 3.3, which equals 2 times the quantity x squared minus 16x plus 64 plus 3.3 equals 2x squared minus 32x. Now, 2 times 64 is 128. We add 3.3, we get 131.3. Check my arithmetic. And there is, well, I've got 2 good equations for h of x. We have this equation, and I shouldn't have closed that parenthesis. That's a little confusing. I mean, an extraneous parenthesis didn't close anything. Okay. Okay. This is called the vertex form of a quadratic function. Just for future reference. And this is the general form, which is ax squared plus bx plus c, which you'll recognize as something you use with the quadratic formula. And I see that the camera has chosen to blur itself out. I think it was doing pretty well up to this point. Let's see if we can get it to focus. Come on, focus. Okay, I'm going to pause for a second and focus the stupid camera. Okay, I don't know what's been recorded and what hasn't. I thought I was recording a minute ago, but let's just go over it again. Okay, I don't know where the camera blurred out, but we have our function g of x, which has been obtained by doubling the distance of every point on the f of x graph, okay, from the x-axis. And we've already seen how that works, and we see that in some detail. Now we shift our usual 8 units horizontally and 3.3 units vertically. And we see that we end up with 611.3 up here, 1011.3 up here, 8, 3.3 here. Now, we call our function h of x, okay? So, you know, I've used orange chalk for h of x, so I'm going to kind of go over the purple and make that graph sort of purple-orange. So that's our h of x graph. And arrows probably unnecessary here. There's our g of x graph. G of x minus 8. Well, g of x is 2f of x. So g of x minus 8 is 2f of x minus 8. And then we add 3.3, that isn't affected. And what's f of x? F of x is x squared. So f of x minus 8 is x minus 8 squared. We have this. We expand the square. Well, we write then h of x equals just what we had in blue here. It's called the vertex form of our parabola. Vertex form because we can easily read off the vertex. It's 8, 3.3. Okay. Now we can expand this and put this into the form 2x squared minus 32x plus 131.3, which is a general form ax squared plus bx plus c of a quadratic, useful if you want to use the quadratic formula, for example. When we square this, we do want to be careful that we don't think that x minus 8 squared is x squared minus 8 squared or x squared plus 8 squared. It's x squared minus 16x plus 64 because there's a distributive law involved in multiplying binomials, okay? Or multinomials. So there's quite a bit about function notation here, quite a bit about transformations. And this is the general transformation of a quadratic function. Okay, there's nothing more you need to do. There's nothing more you can do with our basic transformations. If you can get any quadratic function like this, okay, if you know what quadratic function 1, if you know where 3 points are, well, that comes later. The algebra gets a little, not too bad, but a little bit tougher. Okay, now again, before the camera blurred out, there was something I thought I wanted to say, so let me make sure that I haven't left something out. Okay, now, questions that should immediately rise. Okay, hopefully you would even be thinking ahead a little bit. Say, okay, what if we move the vertex, the red dot, someplace else? What would you have to do? Well, what if you wanted to move the red dot here? Okay. On the scale of this graph, with the coordinates at this point, and what function would you get? What function would you get from the f of x function if you just move the red dot here? What function would you get from the g of x function if you move the red dot here? Okay. Another thing, what if we triple the distance from the x-axis? Here we double the distance from the x-axis. What would change if we tripled the distance? What would change in the picture? What would change in the expressions for the function? And so at this point, you have the tools, hopefully, where you can explore and ask those questions. And then at that point, not before, at that point, you could then take this graph, take this expression, plug it into your graphing calculator or Desmos, and see if the graph doesn't end up with a vertex here, in this point, and all the other points that you would get from what we do, and kind of complete the process. Okay, we don't want to use the calculator. We don't want to use technology to do this. We want to understand this. Then we can use technology to explore and test. And this is a good opportunity to do that. If you do that and do some exploration, let me know about it. What if we cut the distance to the x-axis in half? What if we wanted to flip this thing over the x-axis and make all the distances the same, but on the other side? That would have the effect of flipping the graph. Those are things that I would urge you to think about if you want to excel in this course, and if you're going to get into any mathematically intensive field, okay? Either business, finance, chemistry, physics, engineering, mathematically intensive disciplines. Recommend that you begin not just doing the minimum, and of course, I mean, just doing the minimum, this is a tough course. Just doing the minimum isn't bad, okay? But if you have time and inclination, explore a little bit.